Hello, my name is Coline Devin, and I'm presenting our work on self-supervised goal-conditioned pick-and-place. We explore the problem of goal-conditioned pick-and-place in a simulated robotics environment. The robot arm has a suction cup gripper and must pick objects out of the part tray and place them into the kit. For example, here it picks the purple ball and places it into the kit bin. The problem we're interested in is that, given a goal kit, the robot must decide where to pick and place objects in order to match the goal kit. For example, here the cylinder should be placed into the top corner of the kit in order to improve similarity to the goal. Specifically, we want an approach that will generalize to novel objects and lighting conditions and is learned without human supervision. We use the following self-supervised learning approach. First, the robot chooses a random point into the part tray to grasp at. If the grasp is successful, it records an image of the object from the wrist camera. Then the robot chooses a random point in the kit to place the object. Each grasp gives us 3 images and 3 labeled pixels. We know that the points chosen to grasp and to place at contain the same spot of the same object across the images. All other pixels are very likely to be different objects or different spots within the object. We now use this data to learn a pixel-wise representation of the objects in the bin. We initialize a fully convolutional network which embeds the image into a pixel-wise embedding space. We select the pixel at which the robot grasped to get the embedding of the grasped object. We do the same thing for the other 2 images. In order to train the networks, we use a contrastive learning method where the embeddings at the selected pixels are pushed to be more similar to each other, while the embeddings at other pixels are pushed away. This training method only uses a supervision that the robot can provide to itself. Our contrastive learning method requires a definition of similarity between embeddings. We use the dot product as our similarity and apply regularization to avoid large embedding norms. This loss function is akin to a classification over pixels, where the dot product is the logit of the classification. Once we have learned a good embedding network, we can perform goal condition pick and place. To choose where to pick, we embed each image and calculate which pixel in the part tray embedding will most improve the similarity of the kit to the goal. Similarly, once we have grasped an object, we choose where to place it by, again, optimizing for improved similarity to the goal. Using the wrist image embedding here instead of using the part tray embedding at the grasp point allows us to adjust for any errors during grasping. We perform experiments in simulation by using a variety of textures from the describable textures dataset. The training and validation seen textures are from the same classes, while the validation unseen are from held out texture classes. We test out how well our embedding model generalizes to novel textures. We evaluate our model on the task of localizing objects in the bin from a wrist image containing that object. We find that our model generalizes quite well to novel textures, going from 83% on the trained textures to 70% on the held out textures. There's no difference between the validation seen and the validation unseen. Now we perform goal condition kitting. The green square in the part tray shows where our method chose to pick, and the green square in the goal kit shows where it decided to place. So here this film strip shows the kit before, the goal kit, the part tray, the wrist image after grasping, and the kit after placing. As you can see, the object has been placed into the correct location. As another example, again, the same ordering of images. And you might notice that the bins are all different colors. This is part of our lighting variation that we have both during training and evaluation, and we show that our method is pretty robust to this extreme difference in lighting. Finally, we have a last example where is a much larger number of objects in the part tray. Some limitations in future work of our method is that our method only predicts a position to grasp and place at. It does not predict an orientation. So if the object needed to be rotated before being placed, our method doesn't currently capture that. However, rotating objects in the gripper during data collection could provide orientation level supervision. And finally, while our experiments are all in simulation, our self-supervised approach is compatible with real-world training without a human in the loop. Thank you for listening, and I'm happy to answer questions at the Q&A session.